Hi, hi, hi. So let's get started. It's been a week. I hope you have a good Mid-Autumn Festival. So today we will try to finish the descriptive statistics. Probably we can't finish it. Probably one more week, and because we missed 2 classes, so the first homework will be much delayed until I finish this one. Maybe will be released that on probably Monday or Wednesday, because we haven't finished it yet. Let's quickly review what we have been talking last Wednesday. So just to remind you, what we'll cover last time is we cover how to define data, and particular we focus on standard tendency. We study the mean and some median, and today we should be able to finish the discussion on the median, mode, and dispersion, and end at the shape. And we'll talk about the relationship between the variable covariance coefficient in the next class. So probably we hope able to finish all this thing in this class. So quickly let us review what we have done last time. So last time I guess we discussed what is this mean, right? Adding all the numbers divided by how many of them, right? And we mentioned this graph. I added to the slide because I saw many of you drawing on your iPad. And this one would be saying that, I mean, what is this? The data is x1, x2, x3, x4. And what is the mean, right? Mean is exactly in the middle. In the middle in the sense of distance for all the data to the left, okay, is the x area will be same as the one the right area, which is right distance, which is the blue one. So we just keep moving the x bar until the one those distance from the left same as the distance from the right. Those that the idea of the mean exact location, and that probably remind you this graph is if you have a extreme data point, x bar can move away from the majority of data, right? Suppose x5 is far beyond, very big, then the x bar will be much more than the majority of data. That render sample mean is not very useful measure because it's far away from the center of data, right? And we learn how to solve this problem. There are 2 ways. What we call trimming or winsorizing, right? Trimming is basically exactly take out the outlier, right? Suppose I do the income of the people in Hong Kong, they probably want to take out extreme rich people, right? Then it would make more sense, right? And sometimes you may okay to do winsorizing, right? And just look at the data and just take the top or bottom value by the highest value. I mean, you got so usually 5%, 1%, so on and so forth. And last time we talked about the more interesting than simple average. It's called weighted average, right? It's something you know very well. It's the say grade point average, the GPA, and Hansen index. All these things are weighted average, and you know how to calculate that. And there are 2 more mean, which I mentioned here because I think the next class, next week, we talk about Excel, we talk about the geometric mean, harmonic mean, and they have been useful in various ways, particularly the geometric mean is very useful talking about investment. Okay. And if you have reinvesting opportunity, that in that case the geometric mean is a better measurement. The last time we probably stop in this particular slide, I think, is look at the median, and its median is look at exactly the center of data in terms of ranking. Okay, you just tell me the middle guy. And to remind you, that is, if you have odd number of observations, suppose you have 3 observations, and in that case there's exactly the middle guy, the second one, right? So x1, x2, x3. x2 is exactly the middle guy, right? x2 comes from 2 come from n plus 1 over 2, right? So that's how you get n plus 1 over 2, right? Because we have 3 observation. The guy in the middle is the second guy, right? And if you have 5 observation, right? The middle guy is exactly the third guy, which is 6, right, over 2, right? 5 plus 1 over 2. So it's n plus 1 over 2 is exactly the middle guy, right? So that is how we do the counting, right? It's not n over 2, but rather n plus 1 over 2, which is the middle guy. And and when we have even number of data, then what we're going to do is the mean of the middle 2 guy, right? Suppose you have 4 observations, right? So it will be x1, x2, x3, x4. So you should get x2 and x3, the middle, right? So that's why half of n over 2 plus half of m over 2 plus 1, right? Because you want if n is 4, right? So you want x2 and x3, right? 4 over 2 is 2, right? And 2 plus 1 is 3, so x2 and x3. Okay. So if you don't like this kind of expression, because it looks like depend on n, this would be the one that you would be following, which is the usually what you find in the software. That's how calculate the median, right? Because this is functions round down, this round up, right? And when n is odd, n plus 1 over 2 is exactly integer. So you round up and round down the same thing, right? So end up in this guy, okay? And if you have even number, okay, and this guy will be something 0.5, right? It's 1/2, okay? So you take away the decimal places, so you just forget about the 1, right? So just this guy, right? You just you round up is exactly this guy. So in terms of writing, this is exactly the same, okay? But I mean, it's easy to implement, right? And as a member, this is exactly the middle, regardless of where it is, right? So remember the equation here. There's a free example here. We have 1, 2, 3. The middle guy is 2 because n is 3. 3 plus 1 is 4. 4 over 2 is 2. So it's the second guy, right? So when you have 4 data set, 4 observations, then with the middle 2 guy, which is 2 and 3, because m4, where 4, n is 4. 4 plus 1 is 5. 5 over 2 is 2.5. 2.5 is exactly 2 and 3, middle. Okay. And same here. And do note that these last 2 exercises exactly shows, regardless of how the extreme value behave, median don't change at all. Because we change 4 to 40, doesn't change the things, right? So that's why if the order of the data is same, if you just change the extreme value, it doesn't have any impact on the median. Okay. So that is the idea. So do remind yourself that this is what we said, n plus 1 over 2 rank. And very soon we talk about the quantiles that would be, we'll be using this idea very soon. I think a few minutes later. So before we go to that, then we talk about the mole. Mole is something very simple. I think you learned it in our primary, secondary, high school. And the way we define is slightly different from many classical textbook or the way you learn. We just define, okay, mole will be the data that appear most, okay? And what our definition different from the others is many textbooks they define in the way that if data appear once, there are no more. Okay, so I think it's not very convenient when you write program, right? Because suppose you have 1, 2, 3, 4. Okay, if you follow the classical definition of the mole, then they say that no mole. Okay, but they if appear twice, say if 1, 1, 2, 2, 3, 3, 4, 4, then they have everything is mole. So to make our life easier, so we just define when mole always exists. Okay, if they appear once, or everything mole. Okay, so that's a main difference between our definitions and definitions of other people they're using. But that is not an important difference because of if your data every value only appear once, okay, then mole is not very useful anyway. Okay, and in reality, if your data is like spread like this way, right, that means that very likely your data are continuous data, and in that case you're grouping them, right, and you're grouping them, then it become more like discrete data, and that in this case you would likely to have data appear more than once. So this is just a the way we define, because of when you write our software and other package, then that will be easier. But anyway, I mean, it doesn't really make a big difference. When we have 1, 1, 2, 2, 3, 3, 4, then the mole is 2 and 3. When 2 appear once more, then you have 2. Okay, so mole is easy to calculate, but it's not very stable, right? When you change from this observation to the other one, then you have changed a lot. So it's not very convenient. But the one good thing about the mole is it just the thing appear most, right? It doesn't require to say what is the middle, what is center. When the data don't have idea of ordinal data, right? Remember the data what we have at the beginning, right? Right? When you have discrete data, continuous data, ordinal data, right? You can talk about median, right? When the nominal data, there's no point talking about mean or median, right? Because no distant idea. So in that case, you can only say it's mole, right? So suppose I ask, okay, what is the most common way that people come to the campus, right? There's no point talk about median or mole, right? You can only talk about the mean and median. You can talk about mole, right? Maybe the most common way that people come to the campus is likely to be the subway, right? And that's the thing you can do. You cannot do median or mole, right? You cannot median and mean. You can say that what's average distance from the home to the campus. You can say it. What's the median of distance? You can say it because they are continuous, right? Or if the subway, what is the median or number of the station, right? To take to the campus, you can say it. But mole has, although it's something seems to be very simple and naive, the good thing about this is it doesn't rely on anything about distance, right? Location number doesn't rely about ranking, just asking the most common one. So that is one of the good things is it applies even to ordinal data, nominal data, which is a benefit that mean and mole do not share. Okay, so that is one thing that I want to emphasize. So if may I ask any question? If you have any question, if no, then we'll talk about dispersion. Okay, dispersion. Maybe I just do the full screen. It's better. So so for dispersion, remember we learned the central tendency, mean, median, mole is measuring the location or where the main data would be, right? And dispersion is asking us to how the spread data is asking us how the accuracy of our central tendency measure, right? It's how good is the mean, how good is the median. Here we cannot say how good is the, I mean, still some sense how good is the mode. But of course, all these measure, as you will see, only applies very well for numerical data. I mean, it doesn't really work very well when we talk about it doesn't work very well for categorical data. Say nominal data, ordinal data doesn't work well because talking about distance from the how they spread, right? So because the ordinal has no idea of distance, right? Just bigger the better or smaller, just represent the larger or smaller. So when you talk about dispersion, it's mainly talking about numerical data. When you apply the dispersion on ordinal data, it's kind of like not very useful, somewhat misleading, but anyway. But as I said, most of the time we focus on, or this class focus on numerical data, so it's not a big deal. Okay, so just to remind you that when you try to apply variance or IQR, those things to nominal data or categorical data, should be very careful. What do you mean by that? Okay, we still have some meaning, but it doesn't have a good property that you want to have. Okay, so the first two is very similar. It's very simple measure. It's asking you to look at how the distance between some numbers. Okay, and the last three are almost the same concept. Probably you've learned is basically different from the mean. Okay, but let's go about that. Okay, and just to remind you that these last three measures are related to the mean, so you only use it when the mean is meaningful. Okay, if mean is not meaningful thing there, then looking at these measures are not really useful. Okay, the difference is very simple. The range, you know, is the biggest and the smallest, right? The difference. Okay, the distance. Your data have very large number or very small data, a big outlier, then this is very big, right? One of the drawback or somehow one of the feature of this, maybe good thing or bad thing, is if you outlier, then this range will be exaggerated a lot, right? Maybe good thing or bad thing, but that is the idea. The calculus is very simple, right? Just look at the biggest data minus the smallest data. So I don't think it deserves more discussion. Okay, but do remind you that it's talking about distance between observation, and this is only meaningful your data. The distance is meaningful. Okay, just to remind you. So example would be you have two data set. One that says 1, 2, 3, or 5. The range is the biggest minus smallest, so it's 5 minus 1 is 4. The other one is 50 minus 1 is 49. So you can see that by construction, when you outlier, the range is very large. Okay, and it's a good thing because this tells you a lot of outlier in this model, but sometimes a bad thing here, right? Because it will affected by outlier. Okay, sometimes it's good to detect outlier, but if the two data, one data is very spread, the other is not, but the less spread data outlier, then can be misleading. Okay, because just look at the biggest minus smallest. So the other measure to use where often we see is what we call the interquartile range, IQR. Okay, let me talk about this first. This is the measure. Instead of talking the maximum minimum, we look at some other measure called Q3 and Q1, which we define now. Okay, and the idea is the following. So I think it's good. Where can I? Oh, sorry. So So let's talk about quantiles. The quantiles we have is the following. So consider data like this, X, right? This solid data, right? So we have X1 is here, right? And X2 is here, so on and so forth, until we have Xn, okay? And what we learn is like the distance between X1 to Xn is called the range, okay? And because of you just look at the maximum and the minimum, so it is affected by how the biggest and smallest number changes, right? So you want to avoid this. So what you're going to do is, instead of looking at this, what you're going to do is look at the following. So we will use the idea of median, okay, to look at this case, okay? So probably it's like the following. So what you're going to do is look at the median, okay, median, okay? And median in fact called Q2, which will become clear why it's called Q2. So you just have a bread there, you cut the center, okay, or the cake or the moon cake, whatever you like, cut the center, okay, cut center. That will cut the data into two parts, right? The median will cut data into two halves, first half and the second half, okay? Now median, cut it into two parts. Now, and then you would be talking about the first half, you do the median again, that would become Q1, which is for first quartile. And then you look at the, maybe black again, so okay. Another median again, that is Q3, okay? And we say the distance between Q1 and Q3 is IQR, okay? So that is the, instead of looking at the distance between the biggest and smallest, we're looking at the middle of the first half data, which is Q1, and the middle of second half data is Q3. So instead of looking at Q1, the biggest and the smallest, we look at the first half middle and second half middle, okay? So you can imagine someone would call, this is sometimes they call the maximum is Q4, the minimum is called Q0, okay? So if you use this terminology, then we have range will be Q4 minus Q0, and IQR will be just Q3 minus Q1, okay? And median is Q2, okay? So just to have a telling you how to do that part. Okay, so just to define properly what is Q2, right? Q2 is the median, right? Just as I said, you remember this Q2 is half of n+1, okay? So automatically you can easily see that Q1 will be a quarter of n+1, right? Because this is actually 2/4, okay? And Q3 will be 3/4 n+1, okay? So basically just you cut it into the first quarter, second quarter, and the third quarter, right? And that explains why you call quartiles, right? Because quart means 4, right? Quarter, right? Quaterhedron, quart is 4 means. Tile means squares, right? 4 parts, okay? So divided into 4 parts. So that is the idea, okay? Behind this quartile, instead of looking at the biggest and smallest, but you look at the middle of the first half and middle of the second half and take a difference, okay? So I hope everyone would follow this, okay? So here, the definition looks very simple, right? Just like the difference between the two. But the tricky part is, okay. The tricky part is how do you define this ambiguously, right? Q2 have no problem. How to define Q1 and Q3 is a little bit easier here, we'll discuss. But before we go, then is that okay for a definition? Okay, so I hope that is clear. So the difficulties of this, how to define, this one is, there's no ambiguity. The thing is how to define Q1 and Q3 can be a little bit tricky, okay? To be honest, there are many ways to define Q1 and Q3, okay? And this, all the definition would not be a big difference if n is big, okay? When n is small, different definition, different results, okay? And depending on which continent you study your high school or which country you high school, usually the one you learn in the high school will be either method 1 or method 2, okay? And method 1 or method 2 will exactly depends on the idea of median, okay? You look at median 3 times to calculate Q1 and Q3, okay? Because the first thing you do is the median to go to Q2 and then do 2 median again to find Q1 and Q3, okay? And the difference between method or method 2 is whether the median would include it in your calculation when you do talk about the halves, okay? Because you do the Q2, if Q2 is in the data, whether you should be include them or not, okay? So just to remind, just to tell you, focus on method 1, method 2. Method 1 is cut the data in 2 halves. If median is in the data, so it should be include them. Method 2 do not, okay? So let me show you the example before I go to more complicated version, okay? And the version, the method 3 we will be using looks crazy, but this is the one that you can find Excel. So that's why we look at the method 3, that will be the thing we focus on. And method 2, that's you learn in the high school, okay? At least one of them. So let's look at method 2 first, okay? So method 1 is very simple. First, look at the median of this 1, 2, 3, 4, 5, okay? And obviously you can see because this odd number of data, the median is exactly n plus 1 over 2, right? N is 5, 5 plus 6, so 2 is 3. So the median is exactly the third guy, which is exactly number 3, okay? And the method 1 would say, what's first half, okay? First half would be all the data less than the median and include the median. So you will include the median as well with 1, 2, 3. Do note that here, that's the main difference is method 1, you include 1, 2, 3, okay? Method 2, you don't, okay? And maybe I use other color. Okay, method 2, you don't, okay? And the second half will be, method 1 will be 3, 4, 5, okay? And do note that if you do method 2, you don't include 3, okay? So that's the main difference between these two methods is whether the median should be included or not, okay? And in the method 1, okay, Q1 will be simple because we have 3 numbers. The median exactly middle guy, right? Number 2, okay, number 2. And 3, 4, 5, the median of course is 4, right? Only 3 number. And IQL with different between the 2, 4 minus 2, exactly equal to 2, okay? So that is how you get the IQL when you use the way that you include the median, okay? So it depends on which continent, which country study your high school. Some high school do that. And if you don't include the median, you only have 1 and 2, even number of data, you just take the average, okay? Because average of 1 and 2 give you 1.5, okay? Average of 4, 5 give you 4.5, okay? The IQL with just the difference give you 3, okay? So obviously you can see in different method will lead to different result, okay? Although It's similar in magnitude, but it's not good because different method give you different result, right? But anyway, so this is how you do the IQR using method number 2. And to see the next one, if you have even number of observations in your data set, in that case, method 1 and 2 will make no difference. Okay. The reason is you have 6 data points. The median is exactly the average of the third and the fourth, right? Because 6 plus 1 is 7. 7 over 2 is 3.5. And 3.5 will be the talking about the average of the third and the fourth, right? So third and fourth is 3.5. And in that case, the first half is 1, 2, 3. The second half is 4, 5, 6, right? Because 3.5 is not in the data, right? So you could include anything that is below 3.5 will be first half. Anything above 3.5 will be the second half, okay? In that case, it doesn't really that matter, right? Method 1, method 2, you give you the same IQR, okay? Because 1, 2, 3, the median is 2. 4, 5, 6, the median is 5. So the difference is 3. So when you have even number of observations in your data set, method 1 and 2 make no difference, okay? So this is the way you learn in a high school, okay? So we will talk about the way, a more complicated one. It's the one we use it for our class. The reason why I'm using it is because this is used in Excel, okay? I try to teach you the way that consistent what you saw in Excel, and also it can be found in the software package in R or Python. Do remind you that, as I said, there are many different ways. If you look at Wikipedia or other software, they will tell you that at least there are 9 different ways to do quantiles. The one I picked, this one is, I think this one is they use Excel, and there's some reason why this has been picked. If you want to know, then just do an online search why this is good. But there's some reason why this is a good one. And when you know why we were doing this, then you will think that it's okay. It's a good one. Okay. So just to remind you, we start from here. Okay. So here you can see m plus 1 over 2. Okay. Using some math idea, you know that this number, when you try to calculate, either is integer, okay, or a decimum number end with 0.5, right? Anything divided by 2 is either a whole number or a decimum number end with 0.5, right? So that's no problem. We talk about, that's why when calculating median, right? It's very simple, just average of the two number, right? Is suppose this number n over 2, right? In that case, right? Here is, in that case is n is 6, 6 plus 1 is 7, 7 over 2 is 3.5, right? 3.5 is very simple, just average of the third and the fourth, right? So the problem we have some issue is when divided by 4, okay? If this is whole number, that is not an issue, right? So integer is not an issue. But what if not integer, okay? And from mathematics, actually, you learn there are 3 possibilities, right? If it's not integer, if it's not, will be 0.25, 0.5, and 0.75, right? Which is 1/4, 2/4, and 3/4, right? At the end, right? Just decimal. End up with, when you change it to proper fraction, either it's 1/4, 2/4, which is 1/2, and then 3/4, right? When it is 1/2 or 2/4, it's not easy, right? When it's 1/4, sorry, when it's 2/4, we apply the method we learned when we do median, right? It's halfway of the two, right? So what happened when you have 1/4, right? Suppose your data is end up with 3.25, okay? What can you do? Okay, what are you going to do? Okay, what you're going to do is what we call the interpolation. Maybe I just draw it here to make things easier, right? So go in this way. What we learn is linear interpolation. Okay, this is I, this is xi. Okay, so this is, suppose this is 3, so this is 4, right? So if this is x3 here, okay, and if this is x4 here, okay, what we have said is if we have 3.5, maybe I use another color. Okay, if I have 3.5, okay, what I do is I would do a linear interpolation. Draw a line here. Okay, what we've been doing is like the following. Okay, what is x 3.5, right? Suppose what is x 3.5, right? What we're going is to draw a line and plot here, right? So x 3.5, right, will be half of x3 plus half of x4, right? So that is what we have been doing, right? With a median, if count the 3.5, it's just how we do, right? So the question now comes to what happens if we have the following, right? You have the data now is 3.25, okay? And the other possibility what we have is, you can imagine is 3.75, okay? There are two possibilities, right? Because it's 1/4, 2/4, and 3/4, right? So how can we do this, right? What we're going to do is the same idea of interpolation, right? You just try to figure out what is this number here, right? This will give us 3.25. Okay. So if you learn there's no math, actually I don't think you need, but if you learn the math, then you call the division, right? Proportion ratio. You know how to do it. Okay. But even if you don't do it, let's rely on our geometry here. We rely on what we learned in your high school, what we call similar triangle. Similar triangle. Okay. So what we're going to do is look at what I call similar triangle here. Look at this triangle. And maybe I use orange color. This triangle. Okay, look at this triangle. Okay. This triangle, okay, has the height. Okay. Look at this triangle. Okay. What's the height? This triangle's height is x 3.25 minus x3. Okay. And what is the length, right? The horizontal distance is 3 minus 3, sorry, 3 ton, should be 3.25 minus 3, right? Will be 3.25 minus 3, right? Which is 0.25, okay? Okay, now look at this triangle and look at the very big triangle here. I use purple, okay? Look at this very big triangle again. Okay, look at very big triangle, okay? Look at this very big triangle. What is the height? Okay. The height is just x4 minus x3, right? And what's the horizontal length? It's just 4 minus 3, which is 1. Okay? So obviously, probably you know, the orange triangle is similar to the purple rectangle. Okay? So the ratios should be equalized. Okay? Or if you learn tangent, no tangent, right? It's a right angle triangle. Okay? So this over this should be same as this over there. Okay? Similar triangle. Okay, so what we have is the following. Okay, so look at this similar triangle. The idea will be, look at the purple one, x4 minus x3 over 1 will be same as the height over the base will be same as x 3.5 minus x3 over 0.25, right? Is that clear? Basically, that's a tangent, right? Tangent the same, right? This is a similar triangle. So then you can do the math, okay? That I think that is not the issue because you are in the university now. So I think you can easily see using cross multiplication, right? This guy will be equal to x3 plus 0.25 x4 minus x3. I hope this is okay. I mean, the black one. Is that okay? How to change from the cross multiplication? Oh, okay, I can do. So what we're going to do is 0.25 times this, 1 times this, and you move x3 to the other side. Got it? Okay. So actually, that is not very complicated. Okay, just look at the intuition here. X 3.5. Okay, it's very simple. It's just x3 times the distance between them is 25. Okay, just look at this again. Here is x3. Here is x4. Okay, I'm looking at this 25. Okay, 25 and 75. Okay, so it will be just itself plus 25% of the distance. This x4 plus x3 is the distance between them. Okay, you just, because 0.25 here, you take 25% of the distance. Okay, so you can easily see that if I want x 3.75 will be so that is how you get this formula. Okay, so very soon I will talk about this formula again. Okay, looks a little bit crazy, but that's a formula. Don't worry, this already in your slide. Okay, this already in your slide. So let me go back to here. Okay, so that's why you can see the formula here. Okay, what is the quantile? Okay, so first quantile is 0.7, 1/4. Okay, a quarter will be a quarter times n plus 1. Okay, and you round down to get integer, right? Because remember, it's 3. Say the case is 3.25. You negate the 3. Okay, alpha is just a decimal number. Will be 0.25 of x4 minus x3. Okay, don't worry. Formula looks like crazy, but when you apply it, you find it very simple. Okay, it's not complicated. Okay, so let's look at the example. We do it, then you will know it. Okay, it's not something terrible. It always looks complicated, but when you apply, you know it. It's very simple. Okay, so this is what I mentioned just now, but just more general. Okay, so let's do it step by step. Then you will not be confused. Okay. So in this case, we have 5 data points. Okay, so go to this is. Let's do it slowly because I think some of you are not very happy at the moment. Looks a little bit confused. X is 5, n is 5. Okay, so n plus 1 is 6. Okay, remember what's Q1? Q1 is a quarter of n plus 1 data. Okay, so n plus 1 is 6. 6 over 4 is what? No one tell me. 6 over 4. 6 over 4 for 1.5, right? Is 1.5 theta. Okay? What's 1.5? Remember the formula is x1 plus half or 0.5, 1.5. 0.5 of x2 minus x1. Okay? Right? Remember what we have is here is we have x1, we have x2, but we want x1.5. Okay? So the way is x1 plus 0.5 of x2 minus x1, because it's actually halfway, right? 0.5. So that is a formula, right? So k is exactly the integer, which is 1. Alpha is the decimum point, is 0.5. So that's why we apply this formula. That's how we get 1.5. Okay. So now let's do Q3. Okay. Q3 is n plus 1 times 3 over 4. Okay. So n is 6. 6 times 3 is 18. 18 over 4. Let's do it. Okay. 4, 4, 16, 20, 4.5. Okay. It's 4.5. Okay. 4.5 is what the formula we say is, it is exactly x4 and x5 in the middle, 4.5. Okay. So the formula tells is just like x4 plus 0.5 of x5 minus x4. You just start from beginning and just go halfway of the distance, because you say the halfway, right? 4.5 is 4 and 5 the middle, halfway. So we just start from 4, go the halfway between them, right? Start from 4, halfway between them. Okay, I hope that is more clear. x4 in this case is 4. Okay, halfway of 5 minus 4. Okay, so give you the answer 4.5. Guess you get 3. Is that clear? Don't worry, we will have one more example. Make sure you're clear. Okay, if you're still not clear, when I break, I can go around and answer your question. So don't feel it's not, when you know it, it's very simple, but when you don't know it, it's still a little bit puzzling. Okay, so look at this one. Okay, look at this one again. Okay, so this, how many data you have? N is 6. Okay, so n plus 1 is 7. Okay, so let's do Q1. Q1, remember the formula is 1/4 of n plus 1. Okay, so which is 7 over 4. Okay, 7 over 4. Let's do the division. 4. Okay, 1.75. Okay, according to the formula, is x1 plus 0.75, x2 minus x1. Okay, let me explain this formula again. x1 is here, x2 is here. We want x 1.75. Okay, so what we do is we start from here, we go 0.75 of the whole distance. Is that clear? So this is what the formula is, right? If you look at the formula, what they do is get this, right? From this, k is 1, alpha is 0.75. Okay, k is an integer, the decimum is 0.75. So that's why you have this, or you have all this entry here. So get you 1.75. Okay, so let's get Q3. Okay, Q3 will be the third of n plus 1 theta. Okay, so n plus 1 is 7. 7 times 3 is 21. So we want 21/4. Okay. 4, 5, 20. Okay. 4, 2, 8. 5.25. So it's 5.25 data. Okay. So 5.25 is very simple. We just x the fifth, okay, plus 0.25 of x6 minus x fifth. Explain the reason why again. This is the fifth, and this is the sixth, okay? And we just x 5.25, okay, is we go only a quarter of the whole distance, right? The whole distance is 6 minus 5, right? So we just starting from x5, you go a quarter of the whole distance. So that is what it means, right? So that's give you the answer of, you plug in all the number here, you just put this. The difference is 3.5. Okay, so you can see the difference between this number and that number there. So IQR, different ways to give you different idea. Okay, but I do this is because you understand what Excel gives you. Okay, not because this. I mean, of course, this method is has some appealing thing, right? Because you can see consistent with how we define median, right? Just very simple, just like linear interpolation, right? How you get this? Why would you do this? Is interpolation, right? Just remember the triangle we are doing, right? All the math there, but that is a formula, okay? But that's the one you usually find in the Excel. That's the one you have, okay? So if you ask me what you should do in the assignment or your exam, this is the third method. 1 and 2 just try to explain what you are doing. And of course, when n is large, I mean, 3 method would give you very similar result. You don't have any issue there. Okay, assuming n is very big, you shouldn't see the difference between them. And unless data is very crazy shape, but for our purpose, we just follow what Excel has been doing. We just do this one. Okay, so I hope that would be okay one. So let's have I'll run a little bit. Let's have a 10 minutes break. And then in the meantime, I go around to see if in a question. I'm sure some of you may have questions, but after that, we'll come back to do the various thing on dispersion. So I go around to see if any question. So there's no Let's resume. Some of you asked me, is it always one here? But I said, no, because happen to be just 1, 2, 3, 4, 5, 6, right? This is x6 minus x5. So if I have other number, then it will be other number. Okay, this is not always one. Happen to be in this particular case. Okay, I just simplify calculation here. Okay, so let me erase it. So don't worry, you will be working on this when you have the assignment. Okay, I give you some data you work on. You're working on by your hand. Okay, but only for assignment or for your test, you need to do the hand calculation, right? Because you know what Excel give you this formula. So just without Excel, you have the formula already. But just you to know what is the formula behind. That is the thing I want to show you. Okay. So the next thing I want to talk about is this dot plot. Okay. So you learn the median, Q1, Q3, and the range, right? So one of the very useful thing you can see in the practice is what they call the box plot. It's trying to give you how the data looks like, right? There's a box and Winkel's plot is you will give you the 2n is the minimum and the maximum data. And there's a box here. The middle in the box is called the median. Okay, and this is Q1. This is Q3. Okay, so basically this data give you Q0, Q1, Q2, Q3, and Q4. Okay, and in that case you can see the range from the data, right? This is the range, and this is interquartile range. Okay, so this is a very useful tools. Usually not by its own, usually as a comparison. Okay, you can see in this graph I compare two data set Q1 and Q3. You can easily see how the range look like, right? And how the IQR looks like. And also later you will see how the median looks like, right? And later related to what we learned called skewness, right? Because it's whether the median is closer to Q1 or closer to Q3, right? Whether the median is in the middle of data or not. Okay, symmetric or not. But that will be something we'll talk about later. But this will be a useful tools when you try to show people when the data you have, right? Is it good data or not good data? Okay. The next three thing called variance, standard deviation, and coefficient variation are almost the same thing, but using different measure. Okay. What is this measure? Okay. This measure is only is well defined when your mean is well defined. So because definition is called the average square difference from the mean. Okay, is how your data different from the mean. So basically is the distance from the mean, take the square, sum of them, and divide by n. Okay, so what it is measuring, okay, is asking for each data different mean. Okay, forget about the square. Okay, what about square first? If you don't have the square, there's distance from the mean, right? And if you can consider the difference, okay, and you may ask why I don't take the absolute difference, okay? That actually, if you do this, actually what we call is the average absolute distance. This one actually has a meaning, and this is very useful. sometime when you do machine learning or some computational thing. Okay. The reason why we don't use absolute value, instead we do the square, is because if you learn calculus, you know square is differentiable. Okay. And absolute value is not. Okay. So that's very nice property. A square is easy to handle. And if you learn math, you know absolute value is very difficult to do. But now with computer, this kind of thing is not there. Okay. So, but historically, people focus on this, and this have some property there. Okay. One property here is square, means that the outlier would have much higher value because square, right? Because 1 square is 1, 2 square is 4, 3 square is 9, right? So it means that if you further away from the mean, this will expand a lot, exaggerated. Okay. So that's why this variance is a feature of, if we're far away from mean, there will be a lot. Okay. But anyway, there is an average distance from the mean. Okay. Square distance. Okay. Instead of absolute distance, this square distance. Okay. So this is what we want to know, right? Because that is how each data is different from the mean. Okay. Square the distance. Okay. And you will see why we have 2 different formula here. Okay. You have this formula here and another formula here. Okay. You will ask why we have 2. Okay. And the difference between the 2 is what we call the sample counterpart or sample version has an adjustment factor like n over n plus 1, which is bigger than 1, right? Or have a factor adjustment bigger than 1. Okay. So the reason why we have this will be clear when we go to topic 5 of our course. But to put it in short, why I do that is this will be a better measure when we do a sample. Okay. So what do you mean by that? Okay. Is what we want to know is the variance, which is a average square distance. Okay. If we have every single data we want, suppose Hong Kong government have income of everyone in Hong Kong. Okay. In that case, calculating variance, he should use this one. The government use this one has no problem. Okay. Because she has every single data she wants. Okay. That will be the accurate measure of the variability. That's no problem. Okay. But suppose, which is often the case, is you're a researcher or a company, you only get a sample. Okay. A random sample of the Hong Kong population. Okay. Maybe you do a research, government only give you 10% of data or even 1% of data. Okay. Just like you look at the data in China, it's huge, right? So usually when you try to ask data from the government, Chinese government, they only give you maybe 0.1% or 0.01% because you have a 1.4 billion of people, right? They will never give you the whole data set, right? Because of data security, only give you a small percentage of that. And when you only have a small sample of that, okay, and we're interested in looking at the variance of the whole sample, okay, whole population. In that case, the variance you calculate, if you apply this, it's smaller. So that's why it adjusts bigger. Okay. The reason why is you want to look at the whole thing, right? You only get some small part of it. Okay. So the variation is smaller, right? Because you only get a small part of it. Okay. So that's why you adjust according to this formula. You'll get a better result. Okay. So you have to enlarge your variance. You try to do the calculation to make it better. And what to make it better will be clear when we talk about topic 5. But that's why in the next class we'll talk Excel. Excel, we have the function called they would call this P will be this guy, and we have S will be this guy. Okay. So later you will see, or if you jump ahead to the slide, you will see the 2 different formula. Okay. One is divided by n, the other one is divided by n minus 1. Okay. So it will be more clear why we have The one below when you go to topic 5. But do we remind you that our goal is to measure average distance from the mean. That is our goal, okay? And because try to measure that can have some problem when you have only get a small sample of it, so you do adjustment, okay? And you can easily see that when n is large, okay, n over n minus 1 is very close to 1, okay? So that is when you have large sample, this doesn't really make a difference. When a small sample, this will be a huge difference, okay? So that is one thing, okay? This is asking if the data is more dispersed, then this square is larger, okay? So that is the measurement. Is that a question? I hope everyone learns it. I think this is something you learn it, okay? I just want to explain why you have n and n minus 1, because this probably is not something you would learn in your high school, but the reason why n and n minus 1 we will be more clear when we talk about in the middle of our course. You will learn why this is better, okay? We don't explain it at the moment, but hopefully this will later you understand, okay? Now the remaining is very simple, but we just very quickly go into the calculation. Just quickly, we have 5 observation 1, 2, 3, 4, 5, okay, and the mean will be 3. I think without doubt you would think it's 3 already, right? This is 3 here. So this is how you do in a spreadsheet, or you can do it in the table form, how you do the calculation, right? Just for each observation, okay, listed on a column 1, the mean is on column 2, and column 3 will be taking each observation minus the mean, right? 1 minus 3 is 2, 2 minus 3 is -1, and so on and so forth, right? And the last column will be square of the previous column, right? -2 square, you get 4, -1 square get 1, 0 get square get 0, 1 square get 1, 2 square get 4, right? And the variance will be summation of this over n. So it's adding up all this thing, give you 10 over 5 is 2, right? So if you divide by n minus 1, which is 4, is 2.5, okay? So this gives you the idea that sample variance is always bigger than the population one, okay? Because one is divided by n, one is divided by n minus 1, okay? So I hope this is something you learn very well in your high school. Shouldn't be an issue. Just you need to remember, only thing is population and variance are different. One is divided by n, one is divided by n minus 1. And when you use it in your study, always n minus 1. I think that is very unlikely that you get everything from your data set, okay? Very unlikely, okay? Just almost all the cases use this one, okay? But do remember that you are measuring the average distance from the data. But anyway, so the next 2 observation we were talking about is called the standard deviation and the coefficient of variation, okay? So the standard deviation, why we need that, actually is more often used than the variance, which is the square root of the variance. Is because take the square root, you make sure that the measurement unit is the same as the data, okay? And the reason why this is more meaningful is because of when you have cm, it becomes cm squared, okay? That is a little bit tricky, okay? And especially when you talk about data like, so suppose the GDP is count in terms of million, right? And then the variance will actually become million square, okay? That usually your mind explode, okay? So that's why it's better to use standard deviation to make the thing easy. So the population version is just the square root of the population variance, okay? If you later you see when you look at the Excel, this is called STDEV dot P, right? This is standard deviation dot S. Okay. So the difference is again take a square root of this adjustment. Okay. So as I mentioned, you always use this guy, right? That's a better than the above one. Okay. I don't have anything to say besides this. Okay, because this is simple, and some people call SD, right? This is a standard thing. Okay. I'm not going to talk about any more on this one. Okay. So the next thing is very closely related one. It just do the SD and take from the mean. Okay. Take from the mean. Okay. Divided by the sample mean. Okay. That is dividing them. And usually you multiply by 100, okay, to express it in the percentage form. One of the reasons why you want this is because you want your data, you want it to be without unit, right? Because this is in terms of cm, then you divide by cm, there's no cm, okay? It's useful when you try to compare two different data, right? Suppose one data is measured by centimeter, the other data measured by kilometer, you can still compare, right? Or you can, sometimes you want to look at is it variance or is the variability of the height and the weight are similar, right? You cannot, it's not easy to compare height, right? Which is how tall you are and how heavy you are, right? It's not easy to compare, right? But you try to compare these two, right? Then UC will be a good one, right? Suppose we try to talk about, is it, right? People having more variability in terms of height compared to the weight, right? In that case, you have to use this idea, okay? So I don't think I need to spend more time on this. But let's go to the example we have here. Is suppose the data here 1, 2, 3, 4, 5. The mean is 3. Okay, we know that from the previous example, the variance 2. Okay, or the population 1, and the sample 1 is 2.5. Okay, so exactly we can do the SD version. Take a square of 2, take a square of 2.5, give you this 2 number. Okay, and you try to over them by the mean times 100, then give you the CV. Okay, I'm not going to go detail into it, but that should be not be an issue. Okay, so don't worry, you work on it on your assignment when I give you next week. So you will know, you come back to the example, you work on it. Okay, if you don't know, don't worry, work on that assignment and you know it. Okay, try to do assignment by yourself. At least try it by yourself, right? Copy from your classmate will not helping you. Okay, hopefully you can try work on it by yourself. Okay, and just to let you know, again, Excel has no formula for this too, so you have to derive it by yourself. Okay, but it's easy, right? Because you know this guy, you know the mean, then the formula will not be difficult. But we'll talk about this next week. We'll talk about Excel. Okay, so now we have last 20 minutes. I think we can talk about this thing, skewness and kurtosis. Okay, so far we talk about central tendency, mean, median, mode, and dispersion we talk about 5 measure, range, interquartile range. Okay, they're similar anyway. Variance, standard deviation, and coefficient variation. Okay, the last 3 are very similar anyway. Okay, so now these 5 plus 3 measure, 8 measure are things probably you have learned in your high school already. Okay, so these 2, I think most of you would not have learned it. Okay, but these 2 are very important idea, and it has been a lot of applications. Okay, and ignoring those, actually you will see in my application is a value of many things. Okay, a lot of business value or problems or some something misleading thing happen is because of ignoring kurtosis or skewness. One of the reasons why is it because of in statistics, like which you learn later, is we rely too much on the bell shape. Okay, and when we rely much on bell shape, because bell shape by default is symmetric, right? And if you violate that from the data, you still use the bell shape, it's a problem. Okay? So here the two things is try to measure what is deviation from that in two aspects, whether they're symmetric or whether they're the tail extreme value are more extreme than the bell shape predicts, or less frequent than the bell shape predict. Okay, so these are basically trying to ring the bell. Okay, if the data is sufficiently skewed, not symmetric, or sufficiently has a very big tail. Okay, so you should think twice when I try to apply what we usually the bell shape analysis. Okay, we are unable in this class because of the time constraint, unable to tell you what to do when these two are not, I mean, it's not really bell shape. We require some more statistics, require more skills. But at least you should know when you do analysis, if your data violate these two, you should be careful when we assume things are really normal. Okay, but we cannot in this class go further than that. We just tell you there are two things that you should look after when we try to apply bell shape. Okay, the first thing is skewness. Okay, skewness, the measurement is rather simple. Okay, it's not, it looks crazy. Okay, but let me explain to you that it's not something terrible. Okay, the skewness is here. Look at this formula here first. Okay, look at this formula first, because the other formula just rewriting things from the left hand side. Okay, so look at the numerator. Okay, the numerator actually looks familiar if you are not afraid of math. So here, look at this particular green one. Okay, the red numerator. The difference between the red one, the variance, is just the variance you have square. All right. Now we have, instead of square, you have raised to the power 3 cubic. Okay. So what does that different from the variance is? Variance is square. Square means every time you get positive number, because negative square positive, positive square positive, all positive, right? But when you raise to the power 3, okay, what does that mean? If the number is bigger than the mean, it's positive. Multiply itself 3 times, still positive, right? But if the number is less than the mean, right? Negative. Negative time himself 3 times, okay, will be negative, okay? Which means if the data is way below mean, this measure will be very negative, right? If that measure is way above mean, will be positive, right? So you raise it 3 times. So it's possible that you add them all up, right? Can be very negative, right? Or can be very positive. Okay. And now you know this is going to be if a lot of outlier, right? If there's an outlier, very positive outlier, they're positive. Negative outlier, negative, right? And here is we divide it into sigma over 3. Okay. So this is just a normalization. Just make sure that you don't want your skewness measure affected by the variance, right? Where you don't want to dispersion into that. Okay. You divide them. Okay. You will ask, is it necessary to divide? It's not necessary. You ask why we have this, we Excel do this one. Okay. And you may ask, is only the numerator sufficient? Yes, numerator can already a good measure. But if you want to avoid the measure of dispersion, right? Then you divide them, and that's the Excel do it. And this is one of the good measure, right? Of course, you can maybe just I want to look at the numerator itself, but dividing the dispersion is become a better measure. Okay, so in this case, okay, usually we only care whether it's 0, positive or negative, okay? And of course, if it's a 0 or close to 0, you don't ring the bell, okay? If this is very big, okay, and very small, there's no hard and fast rule is how big is a problem, how small is problem. But if say if you're bigger than 1 or 2 or bigger than 2 or 3, then usually it's a problem, right? Because it's bigger than 3 times of the SD, right? Usually you ring the bell. And if right skew or left skew, what it looks like, let me show the picture to you first. So this is symmetric, right? And this likely the right skew, right? And this left skew, okay? This is more like the income data, right? The income, most people is here, very rich people here, right? There's something like this. And this one is usually what I see at the end of semester. Look at your grade, look at your marks. Usually there's quite a lot of people doing very well, most people doing the average, but only very few people doing very badly, right? So this is something you will see always like this, right? So so this is the shape you would expect. And as I mentioned again, you will use this measure to try to ring the bell whether you use the bell curve is good or not. Okay, if your data shows the skew is very small, close to 0, then no, that's fine. You don't have problem with the data. Otherwise, you would have an issue, right? And one way to solve this problem, right? And remember at the beginning, when your data are a lot of outlier, that's why when you do sensor data or truncated data, then usually once you've done that, usually you've done it properly, the skewness will drop and then you don't have much problem. Because this usually is driven by outlier, right? Outlier is big, then you raise to power 3, then you have some issue, right? Because remember when the beginning, right? Remember when you don't have 3, okay? We don't have 3. You don't have square. You don't have 3. This is 0, right? Because it means exactly center, right? So it must be when you have positive, negative, it must be some number that's very big or very small that's push it up, right? So that means the outlier is at work. Okay, so this is the skew, and I think in the Excel that is this is called skew dot P. Okay, why it's called P? Because this is the population one, and the one you would use it is called in Excel. This is at the end. This one we call the skew in Excel. I don't know why they don't call skew S, but Excel later you will see this called the skew. This is the skew in Excel. Okay, what you're doing is again you multiply by some number bigger than 1. Okay, this number you adjust this by 1. It's bigger than 1. Okay, because the one you calculate is not good, so that's why you adjust. Okay, the reason again is because you want to study this big population, you just collect some sample. In that case, you miss some outlier, right? If you miss some outlier, the skew is smaller. So that's why adjust accordingly. Is that clear? I mean, of course, you don't need to worry about why, but when you always use your data, always use the sample version. So that's it. I mean, unless there's some special reason why you don't use it, but almost always do it, okay? And if you do the sample version, you can have a shortcut like this. Okay. So this is the one we use when usually we do calculation. So this is formula n over n minus 1 over n minus 2, and you raise the power 3 over the sample SD raised to power 3. Okay. So this is the easier formula that we use it. Okay. And do remember that your test is open book, so you don't need to worry about it. So just remind you the text open book. And unfortunately, for the reason that there might be communication between computers or laptop or iPad, I cannot allow you to bring your own electronic equipment. you can print them out and bring to the venue. I know it's not environmental friendly, but I don't want complaint of cheating and everyone have to do an exam again. So if you want the formula, just print out whatever you like and bring. Okay. So don't worry about remember the formula. It's always, you want more formula, you can bring everything there. Okay. So no need to worry about. So there's no cheat sheet. You can bring everything. It's not cheating. It's everything. You can cheat everything. Okay. Just to bring everything you want. Okay. I mean, I don't want to say you only bring 1 page or 2 pages there. It's not convenient. You can bring whatever you like. Okay. Just cannot bring your laptop or iPad. No electronic equipment. You can bring whatever you like, the printer, whatever. Okay. So I don't want to spend time on the formula, just very quickly, because it's not very useful. Okay, so quickly you will do is your column of X, right? Look at the mean and subtract it. It gives you this column and square it like the variance. But now you raise to the power 3. Okay, you get this number. Okay, ends up is 0 because you can see this is exactly what you expect. It's symmetric 1, 2, 3, 4, 5, right? With respect to the mean, everything is same. Okay, so this is the case where this skewness is 0 for this case. Okay, I'm not going to go into detail. If you interested, you can go check it yourself, or you can ask me. Okay, and this case 1, 2, 3, 4, 10. Okay, you should expect the same formula goes ahead, and you should expect the positive skewed, right? Because 10 is like far away from the mean. Okay, which is the mean is 4. Okay, because 20 over 5 is 4. So the mean is 4. This guy is further, further away. And you can see, I'm not going to every single detail. Okay, you can see the sample skewness is 1.6 and population 1 is 1.13. Okay, this is much bigger. Okay, and probably you want to ask, is it the skewness is big enough? Okay, if it is 1 or 2, it's beyond 1, then you must try to think about things. Okay, if beyond 2 or 3, then probably you would be worried. Okay, but at least this one is a little bit slightly 1.5. Yeah, kind of you worry about the bell-shaped apply or not. Okay, but I'm not going to detail the calculation. I think it's fine. If you don't know, you do your assignment. If you're still confused, you can ask me or TA. I'm not going to go to step by step. Is that okay? I mean, it's you're a college student. I don't think I need to go in step by step. Is that okay? Okay. If you still question, I start to conserve the time to talk about the other one. So this is the positive skews. This is negative skews. Okay. And I want to spend time on more interesting thing is why we care about skewness. Okay. And as I said at the beginning, skewness would affecting how you apply the bell shape. Okay. And we often about bell shape, there's a problem. Okay. And one of the reasons why people said the financial crisis in 2007, 2008 is because the credit crunch, right? The subprime mortgage. And why there's a lot of that is because of the people failed to take account into the skewness, right? Because of the fact that suddenly there's a huge risk on that. And the reason is like there are a lot of algorithm trading at that time. The algorithm trading usually, if you know, is they depend on a lot of Gaussian or normal distribution. And in that case, they failed to take the kind of skewness. And that's why when the formula that did not take into account skewness, right? And they underestimate the risk, right? Then that's a problem. Okay. And often we look at mean and variance when I talk about people behavior. And do know that a lot of us I actually don't look at unlikely event that unlikely. Okay. What I mean by that is people have a bias. When you look at small probability event, they would think that more likely than it should be. Okay. Why we want to buy lottery? Okay. It is winning lottery is very unlikely. Okay. But people still buy because why? Because it's unfair bet, right? It's even worse than go to Macau and do the gamble. Okay, but you still want to do it, or because of people would think it's unlikely, but it may happen to me. Okay, so doing lottery is a way to try to attract attention, right? So that's why you would see, you may ask the question, right? Why do lottery? Okay, why the government just say get the money and share equally to everyone? Okay, it's not going to make as happy as it should be, because making lottery can make you expect them more happy than it even in this building. So that's why you can see a lot of people do lottery. Okay, and the next one is related to something recently we call the skewness premium. Okay, in the classical finance theory, right? People look at what we call risk-return trade-off, right? You buy a stock that gives you more return. If the market is efficient, you should expect to carry more risk, right? That is a classical theory since from 60s, right? I feel even earlier, right? High risk, high return, probably you would hear that, right? But the thing is, recent study showing that not just that, actually not just the variance, and actually the skewness also would carry some premium. Okay, so if you want to invest in stock with positive skewness, you need to pay a premium for that. Example, Tesla, Google, all the startup, all the Chinese .com stocks carry huge premium, right? Because you expect they have a lot of upside risk, right? So they can grow crazy. So you're paying extra for that potential to grow. Okay, so that is I think it's the reason 1 or 2 years in the literature in the finance behavior that they actually shown in data that actually exists. Okay, so I mean, I don't think they have real model for now, but I think 5 to 10 years later you will see a big model for that. But it has been shown now is a important thing. Okay, so that is so lastly, I want to talk about this kurtosis. Okay, and don't worry, you can see this formula again, looks crazy. Okay, but if you know the skewness, just this 4 change from 3. Okay, this is just 3 to 4. Okay, nothing deep, just 3 to 4. Okay, so instead of telling you, I mean, there's no mathematically, I think it's simple, right? But what does that mean? Okay, it means it's measuring how big is the tail. Okay, the tail is a lot of things at the end, 2n or not. Okay, and the reason why this measuring the n is because you raise the power 4, so the n will be extremely big, right? When you have very big outlier, that will be expand very big, and because of raised to power 4 is all positive, right? Regardless of the outliers at the right end or the left end, it's raised to power 4. So as long as you have a lot of outlier, then this thing will be very big. Okay, so and then what's the benchmark, right? Skewness, you can negative positive more than 1 or 2. So this skewness kurtosis, the benchmark is the bell shape. The bell shape is 3. Okay, all the bell shape gives you 3. Okay, no matter which bell you're talking about, normal as long as bell is 3. So that's why we define what we call excess kurtosis. Is you always calculate the kurtosis minus 3. Okay, if it's exactly 3, it's the bell shape. If more than 3, it's much fatter. Okay, more extreme event. If less than 3, it's less risky. Okay, let me repeat the statement. If you have data calculate the skewness kurtosis minus 3, if more than 0, then it will be called the fat tail. Okay, or fat tail, or what we call the leptokurtic. If you are less than 0, it's thin tail. Okay, it's leptokurtic. Okay, so look at the graph, it will give you some idea. Okay, so the blue one is the bell shape normal, okay? And the red one is a kurtosis bigger than 0, okay? So the fat tail. And the golden one is the thin tail, okay? So then remember, the fat tail means more extreme event, more likely, okay? So that is the idea. Now, here what we have is, okay, you may ask, okay, I have this formula, okay, how to estimate this will be I don't know if it's crazy or not, but it's a crazy formula. And you ask, why I have this crazy formula here? Because Excel, if you look at Excel, this Excel what give you? If you have Kurt, we'll learn in next class. Kurt actually is this formula, okay? I do understand that you feel this formula crazy, but don't worry, Excel, this is what Excel give you, okay? And you ask why we do this is because the one you use it is not very good, okay? Do note that this is excess kurtosis, okay? If you want to calculate kurtosis, you just add 3 at the end. But you always look at excess kurtosis, so that's because 3 is the benchmark, right? So only important is only this formula, okay? I'm not going to show you this formula. It's easy to see this, right? I don't think you will be wise at the time to go again to go to this, okay? But let me tell you why this is negative kurtosis, right? And you learn this, the bell shape, right? Look at this data, right? The SD is 2.5 square root, okay? So it's 1 point something, right? And if you try to look at the data, the mean is like 3, right? So if you try to look at the data, you see all the data is within 2 SD, right? 2 times of centimeter, because 1 point something and 2 point something, right? 2 SD is 2 point something. So everything within 2 SD, okay? For bell shape, you think more than 2 SD, right? So that's why this kurtosis is less than 0, right? Because it's thinner than the normal, okay? So I want to, probably you can check it out, all the calculation by yourself. I don't think I need to do it. But I want to emphasize on the, in this case, you should expect this one is more skewed than it is positive, right? I don't think I need to go ahead. But do note that one thing I want to emphasize in this calculation is you can see the population is very close to 0. But the sample one is huge, right? So that means that the sample one, the population is not very good measure. You should use the sample one. And that's why Excel, you only have the sample version, don't have population version, okay? That's why the Kurt there's no Kurt.S, that thing, or Kurt.P, okay? So I think finally, I think I overrun, but we'll talk about this. But basically, the reason why the kurtosis is important is because of extreme risk, right? And the financial market, financial bubble are basically underestimating risk. Again, it's the reason why those things would happen. And for insurance company, you have to care about extreme risk of earthquake, say war in Russia, all these things, right? Or COVID is somewhat extreme risk. You have to take care of those, okay? And look at the income, also look at the data. You try to do the bell shape is a problem, okay? So if you look at data, you have a huge kurtosis, then you have to be very careful. And kurtosis is also a good measure of inequality, but I don't think I should go ahead, okay? So let me end here. I will see you next Monday. Sorry for overrun for 1 or 2 minutes.